Hello and welcome to the fourth lecture of Functional Materials Part 2 of Advanced Materials Chemistry course. So in last lectures, what we learned, we will quickly recap. Almost all the practical devices are made using semiconductor materials. We also learned that elemental semiconductors are mainly silicon and germanium only, and then there are compound semiconductors where we use 3, 5, 4, 6, and these are the most commonly used elemental and compound semiconductors in the devices. Then we also know now that there are 4 device building blocks. One is metal semiconductor junction, then PN junctions, then 2 different kind of semiconductors having different band gaps when they are going, then it is called a heterojunction. And then 4th building block is MOS structures. In devices, any one or a combination of these building blocks is used. Then we learn about solar cells and came to know that solar cells are PN junction based devices that converts light into electrical energy. And important parameters for any solar cells are open circuit voltage, short circuit current, fill factor, and efficiency. What is open circuit voltage? That is the maximum voltage which a device can give you. But at that time the current is 0, so it is in the open circuit. Similarly, short circuit current is when you short, and then the maximum current which can be drawn from the device is ISC, and as the device is shorted, so voltage at the terminals will be 0. Then there is a fill factor and efficiency. So fill factor is what is the maximum theoretically possible power if we calculate, and what is the maximum power a practical solar cell will give you. The ratio of this power to the maximum possible theoretical possible power is fill factor. And efficiency is very simple. How much is this maximum power which is being generated by the maximum practical power which is being generated by the solar cell, and the ratio with the input intensity. Then in order to see the devices or solar cell, we came to know that absorption of incident radiation is very crucial, and it is actually one of the most important parameter for material selection process for these photovoltaic devices. Then after absorption, electron hole pairs are generated. The created electron hole pair should be efficiently collected at the electrodes before they recombine. So we have to stop the recombination. For maximum absorption of solar spectrum, multi-junctions can also be used. This we also saw yesterday when we saw a 3-junction devices. Then photovoltaic technologies can be categorized into 3 generations, namely first, second, and third generations, depending upon the material and fabrication technologies utilized. In the first generation solar cell technology, single crystal or polycrystalline materials were used in form of thick wafers. So the wafers is about 300 micron or and even little more. Silicon and gallium arsenide were the most commonly used for this generation. Then thin film based technologies were utilized in the second generation solar cells. So when like in first generation, the thickness was about 300 micron to even more. In the second generation solar cells, the thickness was further reduced to very low, and only very thin films were actually used for the solar cells. The material requirement were reduced and thickness was very small. However, efficiencies were also less. We saw about 7% typical efficiencies. For these, we had amorphous silicon, cadmium telluride, copper indium, gallium diselenide, these are the some typical examples of solar cells which are based on the thin film technology. And these devices are generally have PIN kind of structure. So this is again I tell this is the first generation. Already we have learned very well. Second generation also we have seen almost all these devices. Now today we will learn the third generation, which is called as new and emerging technologies. New and emerging technologies means they are most of the devices which are being studied under this, they are on the laboratory scale only. Only very few are commercially available, but the stability is also an issue. So, in this class of solar cells, what are they important? They are organic solar cells or bulk heterogeneous solar cells, then dye-sensitized solar cells, perovskite solar cells, and quantum dot solar cells. All these we will study today one by one and try to understand what are these devices, how they function, how they are fabricated, what are the advantages, disadvantages of those things we will see in today's lecture. So first is when inorganic was working so fine, why organic is required? Silicon is working fine, even wafers in films technologies, and they are well established. They are working fine. So what are the issues? So issues are number one, these are expensive. When expensive, I say it is relatively expensive. Then high purity materials are needed. You need to control the doping level at a very high level, maybe 10 to the power 19. So that is very high purity materials are needed. That shows. Then fabrication process is complex. You need equipment with expensive equipment, and these devices are not flexible. And some of these solar cells uses toxic materials as cadmium, and some gases like silanes and H2S, etc. are used during the fabrication process. So, organic solar cells were proposed to be a possible alternatives where these problems can be minimized. So, advantage of solar cells, organic solar cells is, first thing is these are low cost. They will be low cost. At present, if you say, because all the new materials, when you fabricate, that particular material is only made on the specific demands of the person who is doing experiments. So at present, you can say those materials are expensive, but once you finalize a material, the mass production of that material will be very, very cheap. So ultimately, these devices will be very, very cheap. That means unbelievably low cost. Then these are good absorbers of light. This is also relative. They are not as good as the absorbers as of the inorganic, but in the relative terms, they absorb sufficient amount of light. When you compare all the things, the cost and all these advantages, in that case, the absorption is. I will show that absorption spectra also, and try to explain a little bit different. So you will realize that even though absorption is low, but still we can call it good absorption for the photovoltaic purpose. Then it is very easy processing. In laboratory, people can make devices, mainly solution processing. Anybody can do it. Then these devices will be flexible because mostly the substrates are also flexible. The molecules, the polymers which are using also shows flexible properties. And then can cover large surface area cost effectively. You can deposit once the deposition process is finalized, optimized. You can deposit over a large surface area without considering the cost so seriously. Then the properties are tunable. Most of these devices use organic semiconductor, and organic semiconductors have tunable properties. You can change the legend, you can change a little bit of the you can say material properties, synthesize that, and then so those properties, like band gap and other important properties can be tuned. And these will be eco-friendly because if you choose biodegradable molecules, then the device is expected to be eco-friendly. Then there are some challenges also with organic devices, which is first is it is evolving technology. It has not yet matured completely. So still so many people are doing experiment at different laboratories or in different industries, but technology has not yet matured completely. So still there is an experimental stage. One is the challenges, and people are doing it so many years, so it is taking time. Then efficiencies are low. And why these are low? When we will see in these next slides that how light is converted, though basic steps are same, but then how charge is transported. So there are some issues. So therefore the efficiency is low. And then degradation and stability is issue. Most of the molecules which are currently being used, these are not very stable and they degrade. So that is another issue. So we will have to find out some molecule which is very stable, doesn't degrade. Then this problem can be solved. And then there's another thing is batch to batch variations, especially when you use organic polymers. So the polymer is actually a monomer and then times n. So that n remains variable. It is not easy to control that. So in other also, like in other molecules also, with organic molecules, if you have one batch, you may make devices and do measurements, you find different than the other batch. So there is a variation. So like in silicon case, it is absolutely standard. If you make the device silicon with a certain purity from buying from anywhere, it will give the same values. However, it is not the case with the organic. You have, but these things can be, with the time, these things can be taken care of. Then another thing is that material purification is difficult, especially in the case of polymers. It is not so straightforward as it was in the inorganic materials. There are standard technologies available in the in the case of inorganic. Though there are many techniques available for organic also, but for these particular molecules or polymers which we are using in the organic, there is no standard purification technique is available. So you have to depend on the whatever we receive from the you can say supply. So these third generation, they are, as it was in the earlier slide also. So they are basically four kind of solar cells. Organic solar cells, call it bulk heterogeneration also, because majority of people are making bulk heterogenetions only. Though there are other also, or you see that. Then dye-sensitized solar cells also, perovskite solar cells, quantum dot solar cells, and tandem solar cells are like in last we have multi-junction solar cells. So tandem is also like one solar cell and one junction and deposition over the another solar cell. So organic semiconductor materials which are being utilized in this fabrication are two kind of organic materials. One are conjugating polymers, and then there are small molecules. So if you have conjugating polymers, then appropriate doping causes delocalization of the pi electrons in these conjugating polymers, and which actually gives you the conducting properties. So some of the important molecules and polymers which are being used very frequently uh, all over the world are like poly-3-hexylthiophene. Lot of work has been done on this particular polymer. Then PPV, then this polyfluorine. So the list is actually very long. These are just those molecules or those polymers which are being used very widely. And then similarly, in the small molecules, pentacene is a very famous molecule. Then rubidium and PCBM. So C60, C70, C80, it is a derivative of fullerene. So this molecule is also very commonly used as an acceptor in the solar cells. So if we summarize, usually organic semiconductors are carbon-based materials possessing semiconductor characteristics. If we have to say organic semiconductors. And atoms within an organic semiconductor molecules are bonded by conjugated pi bonds, while molecules are bonded to each other by weak van der Waals forces as opposed to the giant covalent structure by inorganic semiconductor. So inorganic semiconductor, they are bonding everywhere throughout the crystal. However, in the organic semiconductor case, you have a small chunks everywhere, and those chunks are you can say joined together by the van der Waals forces. So there is no direct continuity, and that is also not a uniformly three-dimensional structure as it was available in case of inorganic semiconductor. So that is also a region of low efficiency. You will see again in organic semiconductor, highest occupied molecular orbital HOMO and lowest unoccupied molecular orbital LUMO are the analogous to the valence and conduction band respectively. But always remember HOMO and LUMO are different and valence band and conduction band are different. Many times, especially I have seen many of the chemistry people confuse themselves with the HOMO LUMO to the valence band and conduction band. Actually, they are different. The width of valence and conduction band is very large, and another thing is they are throughout the entire crystal they are same. However, in case of these orbitals, HOMO and LUMO, they are localized and they are then there are many chunks which are at one place to another place joined by the van der Waals process. So these and the thickness of this is also very low. The thickness of the band of this HOMO band and LUMO band is also very low as compared to the valence band and conduction band. You keep it in mind when you there is a technical difference. So now in other way, if we just see what is the difference between inorganic and organic semiconductor in this slide, I am trying to explain. So in inorganic semiconductors, you have valence band and conduction band. So when light is absorbed, an electron and hole pair is generated, and once an electron is inside a conduction band, it is ballistic. It is actually it belongs to the entire crystal. From one side to another side, it can reach in no time. Only thing is that it has to be separated from this hole. So then there is no question of recombination in this particular system. So so you can imagine it is with a very little efforts after light is absorbed, you are having hole and you are having electron where both of them are independent and they travel independently. So we can call these as free charge carriers also. However, the thing in organic semiconductors is different. As I already said, here you, in place of valence band and conduction band, you have HOMO and LUMO. So this is a small like chunk which is made of. If you can recall the first lecture and initial part of second lecture where we try to explain how the bands are formed. So the width of the band is generally, it depends how many molecules are there in that ordered structure. So here you have small number of molecules in those chunks. So these makes in place of valence conduction mean it makes LUMO and HOMO, and the width is, it depends on how many atoms or molecules are there in that particular state. So then these are held by the you can say van der Waals force. So there is no direct continuity. So suppose you have one you can say one chunk which is having this structure, then you will be having another similar kind of thing which will have the same you can say homolumo structure, and then when if they are absolutely identical, let us imagine they are absolutely identical, but they are held by the van der Waals forces. So since there is no direct continuity between these two, or there is very you can say there is a gap, though even it is very small. So electron, when it is in this state, this can because there is no continuity, it will not directly move to this level from this to this. This can only hop. So the probability of that hopping is also small as compared to when it was in the case of inorganic semiconductor. So movement of this electron and hole become less in these organic semiconductors. So the mobility also becomes low. So if the mobility is low, the charge carriers move slowly, and if they move slowly, in that case, what happens? The there is a more probability of the recombination. So and there is one more thing. Here we call them the free charge carrier. They are electron and hole pair separated to each other. However, here in the case of this, we will never call them separated unless they are physically separated. So if an electron is excited from this state to this state, it will remain because it will not move out of this particular you can say location, and only this much width it can move here and there, but it will remain here only. So we call it a bound pair. So, and this is called as excitant in place of electron hole pair. So now you have in place of electron and hole pair separately, you have here in the case of organic semiconductors, you have excitants. So though there is an electron and hole pair here, but they are bound. They will remain together. It is so first objective or first prime objective is to separate these two. So that electron is separated and hole is separated, and until it remains in this level, it is not possible, because this is very you can say localized range. It is difficult to hold them together for a very long time, and because they are in the same you can say small zone, it is more probable to recombine. So the recombination probability is more in case of organic semiconductor. One is recombination probability, which is more, and the another is the conductivity or mobility becomes low. So this is like typical values. If I say low carrier mobilities for like hole mobility, in case of organic, it's very low. It is around 0.01, less than 0.01, and compared to if you try to compare with the silicon, it is very high. It is nearly 500. Right? So similarly, if you see electron mobility also, it is only 0.1 as compared to 1500 centimeter square per volt second for the silicon. So you see the mobility has reduced drastically. And the reason for this is, like I explained in the previous slide, if you can think a little bit and spend some time, you will be able to realize, yes, the mobility is going to be low because the electrons and holes are not moving so freely. Then carrier diffusion length. What is carrier diffusion length? Is the length the length actually before the electron and hole pair combine. So like in another way, if I try to explain that, if you have a organic, in that case, if you have generated exciton or electron hole pair within 10 to 100 nanometer of that length, it will not move more than that, and it will recombine. However, in the case of silicon, if an electron hole pair is generated, it will move up to 300 micron before it recombine, and this is an average value. So carrier diffusion length is that average value uh, uh, after which the electron hole pair recombines. So carrier diffusion length is very small, you can say within 10 to 100 nanometer, it is going to recombine. So there's no point of having the thickness of a active layer of the solar cell, which is more than 100 nanometer. Here you can have quite large, like 300 micron, which I said the typical wafer thickness. So these values comes from here on. As I said, the thickness of the wafer, and you will see the thickness of these devices. Then carrier lifetime is for silicon, it is 1 millisecond. However, in organic, it is nanosecond, because the diffusion length is low. So there is a more probability of recombination. They recombine more, and the so therefore the lifetime is small. Lifetime is the average time which the carriers spend in excited state before they recombine. So in case of singlet state, it is in nanosecond. However, in triplet state, it is in the order of microseconds. Because why it is 3 order of higher in the triplet state? You may be knowing from the basic transition rules that radiative recombination in triplet state is forbidden. Then stability. Inorganic materials are highly stable compared to organic materials that are generally reactive with atmosphere and also show photo-induced degradation. But these are with the present materials which we are using, but not all organic materials are reactive with atmosphere. But whatever prospective materials are there presently for the photovoltaics, they are almost all of them are reactive to the atmosphere. And there are photo-induced degradation also in the molecules. Then preparation, if you see organic preparation of organic is this, I have already said that flexible and low substrates are there. Room temperature solution processes possible by fabricating these devices. In case of silicon, you need high temperature, energy intensive, and expensive processes. So if I conclude that organic have advantage of low cost and easy processing, but need further development. So yesterday we saw a typical animation for the solar cells of silicon, how they were. Here you will see the typical organic solar cell, how this will be working. The first thing is that there we used to call N-type and P-type, or P-type and N-type. Here in the organic, those molecules are, we call them donor and acceptor. And this donor and acceptor is actually different than what we use in the p-n injection terminology, when we use P phosphorus and we call it as a donor because it is donating electron to the valence band. Here, all those molecules which are replacing, they are in the similar to the P-type materials are called as donors, and other like in acceptor they call as in place of N they call as acceptor. So now imagine, so you have just joined one donor and one acceptor together, and you have made two connections with the two different metal elements. So these are like one will be cathode, one will be anode. So now this I can say very basic device of a polymer. Just replacing silicon N-type and P-type to donor and acceptor, and I put anode and cathode. There we use the same connection. Here we will use different anode and cathode. Normally different anode and cathode metals are used here. It depends on what it depends. It depends on the you can say work function and then energy level of these donors and acceptor relatives. So under thermal equilibrium, when we join them together, it was like this initially. When we join them, it becomes like this. Provided this is a very small distance, this is also very small distance. If they are very long, then it will not apply because there will not be movement of the you can say carriers throughout. Carrier should move from this point. So there should be actually a definite mobility when you want to draw such Fermi level in thermal equilibrium to make it uniform. And there is another point when this is illuminated in that particular time and when the carriers are generated, this will not hold good. So then in that case, this Fermi level will not remain flat. So just keep it in mind. This illustration is only to give you an idea how these solar cells are actually working. So now when photon falls, let us say it falls on the donor side. It can be in the acceptor side also. The things will remain same. So now, though electron and hole pair are generated, but they will remain bound. They will not. They are not separated. Like in case of inorganic, they were separated. Electron and hole pair were separated. Electron was traveling separate means with a little bit of you can say application of potential. It was able to accept that energy and move higher into a particular conduction band. Means accept that energy, increase the energy, move it higher into conduction band, and have energy so move a different plate also. Here now they are bound together, and when they are bound together, there is another problem. Now they are charge neutral. So if they are charge neutral, in that case, even if their built-in potential is, you can say some built-in potential is there because of the difference of work function between anode and cathode. However, because it's charge neutral, it will not have any effect of the potential. So why it will not have any effect of potential? Because negative will be pulled towards one side, pole will be pulled towards another side, and the force depends only on the charge, and charge is absolutely zero. Net charge is absolutely zero, so it will not move in any particular direction because of the application of or because of this built-in potential. So then how it will move? It will randomly move. As I said, it can move randomly. Some will move this side, some will move this side, some will move this side, some will move this side. So the probability of moving it in all 4-5 direction is same because it's charge neutral. So it can move any direction. And then there is a because it remains together. During this period, there is strong probability that it can recombine. So if it recombine, that is lost. So then, so all these problems are, you can say, they are reducing the efficiency of overall solar cell. Now let us assume the most optimistic way that it moves in this direction, which we prefer. So it moves and it reaches at the boundary. When it reaches at the boundary, it sees this much difference of energy, which work as a activation energy or which which energy which is compel this electron hole pair to separate, because coming electron from this point to this point, it is actually reducing the energy. Every system in this world try to reduce energy and want to stay in the minimum energy state. So this much difference of this energy will provide, you can say, provide favor to so that this electron and hole should get separated. Now, still there is a probability that this can back recombine also. At this point also it can be reformed. So now let us assume our most favorable condition, which is also very low probable, but it has separated. Now, once it is separated, it has become electron and hole, both are become separate. Now, whatever built-in potential was there, they will see it and act in that potential. So now they will move towards their respective electrodes, and then once they are reached the electrodes, and that is connected to the external circuit, so then they will move in the external loop. Now, when they were here at the time, though they were separated, there is a possibility, good possibility that can recombine. This is called as the back recombination. So I hope it will be clear. How this solar cell is working? It is similar like inorganic. So now let us try to see if we can make in the same way as we were making the silicon solar cell, which was working very fine. They are very good, working for so many years. I have given an example like 40 years, prove the reliability of 40 years. So we do the same thing. We do the same experiment. What we do, we like here N type, we use acceptor. In P type, in place of P type, we use a donor material. We put together. So we have a donor material. Above that, we deposit an acceptor material, and above that, we deposit an cathode and anode below this TCO, or you can say TCO itself is conducting. So then you have two electrodes are connected as they were connected here. So will it work? So this was the first, you can say, basic device, which was an organic device made, or you can say an organic solar cell was made. This was the first configuration. Structure was similar to p-n junction solar cell, and this device is called as the bi-layer devices because it has two layers. So now let us see what was the problem in this and how it performs. So first thing is that the diffusion length, the typical diffusion length is only about 20 nanometer. So when first thing is that whenever radiation falls at the junction, electron hole pair or exciton will be generated in that case, and the diffusion length of the exciton is very low. So within 20 nanometer of that, they are going to recombine. So if they are going to recombine within 20 nanometer of this movement, like during this, you can say volume only, this and this volume only, then how they will reach at the electrode? So they will. So it is very, very difficult for this electron hole pair, even if they are separated, to reach at the electrodes. So like all those excitons which were created here or which were created here, they are expected to be lost. So majority of this volume of this solar cell was actually not active, non-active. So active layer will only be this much small. So because of this problem, the efficiency of this solar cell was very, very low. And when I have written 1%, it is also of the best possible device in those cases. And otherwise, the efficiency was 0.00, 0.02, something like that. And in most of the papers, if you will see of those times, the efficiencies were very low of these bilayer devices. So these were, this is the first kind of device, organic device. This was bilayer device. The experiments were done for a few years and then it was stopped. So what we should do to overcome this problem? Then it was like blending. If you blend them together, this next approach was of the bending approach, and this was like, if we cannot increase the excitant diffusion length, can we try to bring junction nearer by blending? See, blending is you mix both of them together in place of depositing. In place of depositing like this here and here, you just blend them. So then how this blending is done is like that. You mix both donor and acceptor with each other and mix them for many days, so that these molecules, so both these materials are very, you can say, very good with a very good mixing. So now if they are having a very good mixing, what you will see every donor will have a nearby acceptor. So that problem of that distance is removed. But another problem was created now. Let us see first that we will discuss that problem first. Let us assume in ideal case there is similar kind of ideal. All these three pictures are just to give a clear picture, but they are effectively same. So it is like, suppose this is like donor and this blue is donor and this yellow is acceptor. So now you see if a photon is falling here somewhere, so it will create an exciton. So this exciton, it has to move only this much distance, which is very near. Once it reach here, it will at boundary the necessary there is the energy difference which will give the next necessary activate some energy, and this electron and hole pair will be separated. So now you have an electron and you have a hole here, this place. So this hole, now once they are separated, that will move by this path and it will reach at the electrode. Similarly, the hole will move this path and it will reach at the electrode. So one problem is solved, that there is not now very big difference between the donor and acceptor. Each donor is having a very you can say close by acceptor. So boundaries are now very near. So there is a diffusion length problem, which was the problem which was coming because of the diffusion length has been now minimized. But there could be now another problem. You see, just see this. You have one electrode here, you have another electrode here, and if you see this part, see, this is actually having contact from this surface to this surface. So one type of material which is having a contact between one electrode to another electrode will make it short. So if the device is shorted, then how it will work? Then it will not work. So then you have to find out some other solution to add into this. So one is by mixing together, you brought them very close to each other. Same thing is I have shown. This is the same example here. Here light falls, electron and hole pair generated. So hole moves here, it goes like this, and electron goes in this. Electron transport and hole transported. So then, as I said, there is one problem of this kind of shorting issue. So this will actually reduce the efficiency, and it will make your device user. So now another concept come to outcome, that is of the hole conductor and electron conductor. Hole conductors and electron conductors are those you can say they are different kind of materials. By now we understand very well that electrons moves only when there is a energy level allowed for them. So if there is one line corresponding to that particular energy and electron it is allowed for that particular energy level, then only an electron can come at and move from this place to this place. The energy allowed energy levels only. If it is not allowed, electron will not accept the energy and electron will not move there. So there are certain, now we know that there is a hole or there is an electron. We know from the earlier band graph by the animation, we know that what is the level of the acceptor and what is the level of the donor. The HOMO level of the donor and LUMO level of the acceptor. So typically near to that particular level only, if we find a material which is very near to that level and we make a contact with that, in that case what it will do, it will allow only electrons from move, you can say, through that material. Holes will not move because there is no energy level which is in that material which will favor the movement of holes. So these kind of materials are called as electron hole selective contacts, and also called as these transport materials, these hole trans. So I will just try to same thing which I said, try to explain here also. So suppose this is an energy level of the electron hole pairs are generated. Now if I have a material like this, if the material is like this, and this I can find out at the level of the electron is, you can say one electron level is here, which is very close to this electronic level. So now electron can come from this place to this place and move, and then can move. However, the hole, because it requires a lot of you can say energy to move from here to here, and therefore electron will not move through this material. So this material is you can call an electron selective contact or electron conductor. So it will only you can say electron and this is called as electron transporting material also. Similarly, if you have a like a material, if you find a material which is having energy level like this and this, so you can see this is very close to the energy level which was of the energy level for hole. So now it can come from here to here, and it can so only hole will move. This electron will not move here. So so it is because there is a large energy difference between these. So so this material will be called as the hole transporting material. So now we have a concept of number one. We have developed a concept of first bilayer. Then we saw there are a lot of problems. Then we developed a approach of blending called as bulk heterojunction, where we saw some problems, and then we have added now two more things, which are electron transporting material and hole transporting material. So a overall solar cell should be like this. You have a like active layer. Active layer is that blend of the donor and acceptor that we call active layer. So now you have an active layer which is deposited like that, and then you make such kind of like assemblies. In those assemblies, you have deposited like one is from the hole transporting material, or another is from the electron transporting material, or hole transporting material and electron transporting material. And then it is now easy. If electron, you can say electron hole pair, if they do not recombine, they reach the boundary and they get separated into hole and electrons. So electron will move only through, hole will not move through this, and you can say hole will move through this and electron will not move through this. With this, you can make now the devices. So advantage of this advantage of this bulk heterojunction approach is they have high surface area. This advantage is basically using this kind of assemblies, finger kind of assemblies, and this allows the use of locally in absorbers. So just put absorber over there, and that absorber will be also be over the long area. And then the problem is of the see in such kind of assembly, it is very difficult to have thickness control. So then you can have at different points you will be having different thicknesses. You may have pinholes also, and this therefore the quality is degradable. So similar like yesterday, we can see in case of organic solar cell. So exactly same thing. So if sunlight falls on a solar cell device, if it reflects, it is lost. If it gets coupled to solar cell, and if photon transmits, if it is not absorbed, there I said if the band gap is not suitable, or if the energy of the photon is less than the band gap energy, it will simply be transmitted. And another thing is, if thickness is not sufficient, then also it will be transmitted. So although the photon entered, it was not reflected, it enters the material. However, it was not absorbed. So that is also a loss. So these two loss, if somehow the photon was absorbed, So let us say in case of absorption, first thing is now here in place of free charges, you are creating exciton. So this exciton now they can recombine, and there is a very, you can say, high probability that these excitons recombine as compared to inorganic. So if they recombine, it is again a loss. But if somehow they have reached the boundary and they have created free charges, in that case, they still can recombine, back recombine, as I showed in that animation, that electrons. But the probability of back recombination is low. So that is not like very serious issue. But here the exciton recombination is serious. So even serious issue. So if those recombine by back, then it is also a loss. And if they have, you have separated those by building field, in that case, if charge also recombine, though they do not be, they may not be, you can say, radiative recombination because of surface, you can say levels also. There are many reasons why the charge can also recombine there. So that is also a loss. And if they are finally collected at the electrodes, then we can say, okay, our purpose of the solar cell is completed. So all these loss mechanisms need to be minimized. That should be our purpose of doing all the experiments, doing, you can say, all the development work in the case of organic solar cells, is how to reduce these losses. So now I will just touch upon the quantum efficiency. Quantum efficiency is the ratio of number of carriers collected by the solar cell to the number of photons of a given energy incident on the solar cell. So how many number of photons are, you can say, received or how many of photons are absorbed by the surface, by the solar cell, and how many number of electron and hole pair are generated. Suppose you absorb one photon in the solar cell and you get one electron hole pair, then you can say the internal quantum efficiency of my solar cell is 100%. This is different than the efficiency which was the general efficiency. What was that? That was the how much input intensity, light intensity is falling. That was for one sun, it was 100 milliwatt per centimeter square. Here what we are saying, it is how many number of photons are being converted into electron and hole pair. So this difference you keep in mind. Quantum efficiency, many people get confused between quantum efficiency and solar cell efficiency. Quantum efficiency is also of solar cell only, but it is photon related. How many photons are incident on the solar cell and how many electron and hole pairs are generated. So then there are two like external quantum efficiency and internal quantum efficiency. So if you just remove, you can say the internal quantum efficiency comes into picture when light has actually been absorbed. However, the external quantum efficiency, that also take of, you can say, how many photons were sent. How many photons were sent to the solar cell? If those reflected 9 or you can say 10 were reflected, it will not, it will account for those also. However, for internal quantum efficiency, when they have actually been absorbed, then only it will be accounted. So suppose I sent 10 photons, one photon was reflected and 10 photons were absorbed by the solar cell. In that case, out of those 10, I will say, you can say 9 only, because 9 was absorbed. Out of those 9 electron and hole pairs were generated. So my internal quantum efficiency will be 100% because 9 photons were absorbed. And out of them, you have received 9 electron and hole pair. However, my external quantum efficiency will be 90% because I have received 9 electron hole pair when actually, I have sent 10 photons to that particular solar cell. So internal means when it is absorbed, how many photons were absorbed, how many electron hole pairs were generated. In external, it is how many were sent to that. Then there are some other like optical efficiency, light absorption efficiency. This is exciton diffusion efficiency. This is charge transfer efficiency, and this is charge collection efficiency. Very quickly, we will go into it. So this is a typical absorption spectrum of a molecule, this is actually a polymer. This is a P3ST polymer, which is very commonly used in the solar cells, organic solar cells. This is of the PCBM, which is acceptor molecule, which is also used very commonly. Actually, P3ST PCBM is the most studied solar cell, and almost every laboratory start doing experiments from this organic solar cells on organic solar cells. So this is a you can say typical spectrum of my you can say the solar spectrum. Now there is one difference if you notice. When you had a inorganic material where the band was very you can say big or width was very large, in that case, if the absorption or you can say the radiation falls with energy which is more than the band gap. In that case, entire energy will be absorbed. So if you have you can say illuminate this spectrum to the silicon, what will happen? This is the, you can say 1100 nanometer is typically wavelength corresponding to 1.12 electron volt. So what will happen? All energies which are having more than this 1.12 electron energy. So wavelength will be lower for all of them. So then all of them will be absorbed. So this entire spectrum will be absorbed, and all the energies which are higher on all, that means all the wavelengths which are lower than this will invariably be absorbed by the silicon. But here, if you see in the molecule or in the case of polymer, see for P3ST, this is the absorption spectrum. For another, you can say polymer, this is also my absorption spectrum. So if I try to say the band gap will be somewhere here, the energy corresponding to the wavelength, the band gap will be here, and the corresponding wavelength should be 550 nanometer. So if you see, even my energy, when energy was low, actually, if you see theoretically, the band gap generally is calculated from this when there is an onset. So but we are qualitatively studying and trying to explain you in a simple way. So if you see this increase of the absorption is, we can understand. So that because as wavelength is increasing, energy is more, so there will be more photon energy is more than the band gap. However, so therefore it need to be absorbed. But what explains this part? It should not come down. When the energy is more than band gap, it should invariably be absorbed. It was always the case when the silicon was there, but it is not in the case of these polymers. Can someone explain me the reason how? I have already, when I started, I have just given an answer. So the reason is because the band is very large there, and here the band is very small. In case of this, the band is very small. So when you start energy, like suppose we have typical width is like this, and here we have typical width is like that. this is delta E, this is delta E1, this is delta E2. So when some if I zoom it here, so when a electron is here at the bottom of this band, and when electron is here at the top of this band, and when it is excited from this to this, it will take this energy, suppose. Now, same thing I have zoomed. It is for organic I am talking, not inorganic. So this was this case. It started from here, and then it will go on increasing. It will go on increasing. It will go on increasing, and then the maximum energy will be corresponding to this particular. When from this bottom you have raised an electron to the top. Now, suppose you have an electron here and you have given energy which is slightly more than this energy. What will happen? It is not going to accept that. It is not going to absorb that, and it will very simply be transmitted. Same thing is being, you can say, seen here in this curve. So it is in this curve what we are seeing now. This has reached, and now after this you have actually reached at this energy. Now if you increase further, there is actually forbidden band. This energy is not allowed, and this is applicable for the organic only. If you see in case of inorganic, what is there? If the inorganic, same if I explain, this is normally this only, but after if you reach here, then there is actually continuum. After that, it is mostly ionization state, and then electron become totally free. It can even go out of the, you can say, material. So if it goes into it. So this is the absorption. So only this much amount of, you can say, spectral portion can be absorbed, and therefore the efficiency, whatever you have absorbed, you will get efficiency accordingly. So absorption is low, so efficiency is going to be low. So this depends on the wavelength. So it depends on the band gap. So one thing what I can do, I make it little bit width. What we need to do to you can say increase the width of the band is to have more and more number of the molecules in like crystalline kind of structure. So you have some more crystalline kind of structure. And another thing is that you can have low band gap material. If you have low band gap material, so and your bandwidth is large, in that case you can absorb this entire spectrum. So let us see whether low band gap material will solve our problem. So yesterday we saw there was, I think I asked the question also. So silicon is, in compared to silicon, germanium is low band gap material. So if you make solar cells using germanium, it will absorb more obviously, and so it will be falling somewhere here, somewhere here. So this spectrum which was left by the silicon will also be absorbed by germanium. So will it be giving you more efficient solar cell? That let us see. So by this you can say these three figures I will try to quickly explain. So in case of this solar cell, the typical voltage or VOC is estimated by the difference of this level to this level. And this comes from the basically it will give you a kind of built-in potential also. So if there is a electron, that electron is there inside that, and it is facing this much amount of built-in potential, in that case it can move faster here. Although the absorption will be less, but whatever electron and hole pair are generated, they will be you can say collected if the voltage is more. So if you can say the band gap, if you reduce the band gap, what will happen? This voltage will be reduced. So there will be a net loss of voltage. If there is a net loss of voltage, the pulling effect of this electron will actually be reduced. And then there is a loss of electron transfer also. If they are not matching exactly here, then electron transfer will not be that efficient. So low band gap material will not actually solve all the problems, and because there will be less voltage. So I like one example I given yesterday. If I can use metal is having zero band gap, so it will absorb all the radiation if the thickness is sufficient. So, but there will not be actually any built-in potential which can pull those electron or which can separate those electron hole pairs. The electron hole pairs will be generated definitely, and entire spectrum will be absorbed. But it will not be of any use if they cannot be separated, because after some time they will remain there and they will recombine. Now, next is excitant. So this part, I think whatever I explained, it is clear to you. Now, next part is excitant dissociation efficiency. So excitant, we now very well know they are bound pair. So, and when they reach at the boundary, they, you can say they can either recombine back, or they can give a radiative recombination in form of photoluminescence. They can back recombine also, and they can get separated also. So this slide gives you an idea of the time scale. So if you see of this particular molecule, this is PPV is the, what is the PPV is the polymer, and this is the acceptor. So this is donor and this is acceptor. So now a electron hole pair, no, sorry, excitant has come to the boundary. Now the probability, or you can say the time scale for this transition is of the order of 50 femtosecond. So it will take very fast. However, the transition of like the back transition, or the photoluminescence, or you can say not back here, it is actually recombination only. It is normal recombination. Back is here. So the time scale is nanosecond. So this is the probability of this transition is, or you can say the separation of electron hole pair is 1000 times more than the recombination. And for like back recombination, once they are separated, electron and hole pair, the excitant is now separated into electron and hole pair. The probability of, you can say, recombining back is even less. It is of the, you can say, even 1000 times less probable than the radiative recombination. So it is more probable that it will actually recombine. So if we need to define, this is I just explained if excitant is created, whether it will be dissociated or not, how we will define it. This is like ratio of number of excitants reaching interface to the total number of excitants created defines excitant dissociation efficiency. In this, what we have assumed that all the excitants which reach at the interface will be dissociated in electron hole pairs. Whatever will not be dissociated or recombined, they are very, very low. So suppose they are 10,000, out of them, those 10,000, only few, like 10 will recombine by both these persons. Out of them, 990 will be dissociated. But it has to reach. So we just see the difference. Yeah, means the definition. Definition doesn't say here. Definition say those excitants which are created. The ratio of number of excitants that reach interfaces to the total number of excitants created anywhere. Once it reaches, we presume that it will be separated. Then charge transfer efficiency is defined as electron and holes drift towards electrodes. On the way, they may get trapped or recombined. That is another kind of recombination. So the ratio of total charge reaching electrode to total conducting charge carriers created at the interface defines the charge transfer efficiency. So now you have all kind of efficiencies. You have you multiply with each other, and you can get the total efficiency, quantum efficiency of the solar cell. So now there are certain materials which are very commonly used. These are ITO and FTO. These are for the transparent conducting of oxide material. For a transparent conducting oxide, these are see normally all the conductors. I think I already explained this earlier lecture, but I once again normally all the conductors are does not transmit any light. They absorb entire light because they absorb every amount of radiation, and electron or the energy level of the electron is allowed in there. So it will absorb all radiation, and electron hole pair will be generated in all the cases, but they will not be separated. So therefore since they absorb radiation, they will not transmit it. Very simple. So, but there are certain materials that is ITO, FTO, and there are zinc oxide based also, which are conducting but transparent, because conductivity in those materials are by a different process, and that is the vacancy based. So vacancy was created, the vacancy. So FTO is thermally more stable, but has a higher sheet resistance and somewhat lower transmission. Aluminum doped zinc oxide is also an option, but not commonly used. So in like laboratory, we use FTO, and like bulk heterojunction, most commonly ITO is used for DSSC that we used to use. So for active layers, there are different polymers for donors: MDMO, PPV, MDMO, PPV, P3HT, metal phthalocyanine, and all these. And for acceptors, perilines, fullerenes, PCBM. Most of the time, especially in our lab, we use PCBM. 90% of the time, PCBM. And then for electron transport and hole blocking layer, there are certain like we use lithium chloride, but people use the other you can say these chemicals also. And for hole transporting layers, we use P dot PSS, and in some cases these also, but in different layers. And all these things are which material you need to use as hole transporting layer, which material you need to use as electron transport layer. It depends on the energy levels of the materials which you have used in the blend, especially the donors and etc. For back contacts, again, like aluminium, gold, calcium, silver, and this also which one will be used as the cathode, which one will be used as the anode, that will also depend from the, in that side, which is the you can say what is the work function of this, and what is the energy level of the particular you can say donor or acceptor. They should be matching in order to use. And what are the you can say fabrication techniques? PVD, CVD, and like LB also. Solution techniques like spin casting, Doppler bleeding, self-assembly, and spray also are very commonly used. Then what are the problems? These are small absorption width. As I have explained you in detail, you will have a clear, will be having a very clear idea by now. Should be having a clear idea. And then small absorption width of known material. An alternative could be used for the multi-layer. So one is like we did in our lab, we deposit because one layer has small thickness, so absorption is less. So we deposit one layer over the another layer, and increase the absorption. Then efficiencies are lower. That is a common problem, and on the efficiencies are lower because of so many issues I explained. So people are trying to increase. Then for the cells made from organic molecules have short life so far because these molecules are not very stable, and some of them when they are exposed to light, they are also degrade. So this is just like how a bulk heterojunction typical layer is made. It is like Yeah, this is ITO. For that ITO, you put a thin layer of HTL, then a thin layer of now then about 100 nanometer layer of the active layer, blended PCST, PCBM, then about very small, very thin layer of electron transporting layer, that is ETL, and then a back contact of electron aluminum, because aluminum level matches with the level of the acceptor of that assembly. And then I have a function also, like I showed yesterday, that will clear. Oh, let me quickly go. So this is full process, like ITO film pattern by wet chemical etching. Uh, I have given it in full details, so that if some of you want to make the solar cell in your lab, you can follow this process, and uh, 90 times out of 100 attempts you will be successful. So just you pattern it using the simple acid treatment at 50 degrees centigrade. Then whole transport layer of PEDOT PSS is deposited by spin coating. Then after spin coating, because PEDOT PSS has little bit of moisture also, so it is annealed at 120 degrees centigrade for about 2 to 3 hours. Then active layers of donors and acceptor materials, that is P3ST, PCBM, they are made together by blending in 1:1 ratio, and with blending, if this would be, you can say, um, 20 milligram per ml in trichlorobenzene. And this blending is we do it for about 20 days continuous blending using the magnetic stirring. Then this blend was deposited by spin coating in the glow box, because you cannot expose this material directly to the atmosphere. The moisture and presence of moisture and oxygen degrades materials, and therefore if entire thing is done inside a glow box where oxygen and uh, moisture both are controlled up to less than 1 ppm level. Then thermal evaporation is done by depositing aluminum back electrodes by shadow masking. And so entire all these things starting from the except this one, this is done outside. Everything is done inside only, including the back electrode thermal evaporation, and measurement also is done inside. And then the device is sealed and then taken out for the stability testing. So this I will just in a animation I will show. So normally when we buy ITO coated glass substrate, it is like that. You have a glass over there, and ITO is that yellow color imaging. So yellow color is ITO. The work function is, or you can say the energy level is -5.1, nearly -5.1 eV. So with that, as I said, chemical etching by using the acid we do, and we remove certain part of from this surface, and we get this kind of I can say. Then we deposit PEDOT PSS by spin coating, and then above that we deposit active layer of PCST PCBM, which was blend after blending for nearly 1 month, 20 to 30 days. And then after that, a very thin layer of lithium chloride, that is electron transport layer. So this is electron transport layer, this is hole transport layer, this is your active layer, this is your one electrode, the other electrode is deposited by shadow masking. So this way, now you see, you can, in the simple, in this geometry, you have made 9 independent devices. You can connect this point and this point, and then you can see, but just imagine this matrix, and you will have 9 independent devices. So in the same experiment, when you are doing experiment, like for research purposes, uh, there is a possibility that your device may short, you may have. So in such assembly, your efforts are not wasted. Out of these 9, you will have 6 to 7 devices which are working, which are not shorted. So this is for the making. Now the contacts are made from between this aluminum and actually this the IT. So connect ITO with this aluminum, and then the process is let's take this date. It is actually may not be required by now. You have already understood how these are working. So then afterwards, when the measurement is done, then device is sealed and then electrical connections are made, and afterwards we take it out. These are some of the photographs, typical photographs which are taken out, which are taken during the fabrication process in our lab only. So these are actual or real photographs. So if I say you will not be able to see ITO because that is the transparent. And so, but however, these line strips you can see, these strips belongs to your aluminum, and similarly on the other side you will have. So now you will have similar kind of strip like this. To at present, what I am measuring, if I made such kind of connection, I am measuring a device which is somewhere here. This is the same thing I have shown. So these are some of the flexible devices which we have made in our lab. So it is 2-inch by 2-inch flexible solar cells. And this is a module. We have many, you can say, small devices are made, and they are actually joined together, some series, some in parallel, so that we can make a module which can be used to give higher voltage, because in practical devices you need higher voltage and some good amount of current. So this module which I am showing you here has given 15 volt and 0.3 milliampere, and we use this module to charge batteries also. We and run the a small DC fan also, and to illuminate some LEDs also. So those kind of things we demonstrated. So this was as far as the polymer or bulk hydrogen solar cells are concerned. Next category of solar cells comes as dye-sensitized solar cells. So dye-sensitized solar cells differs from conventional organic cells in a way that dye is used for initial absorption of sunlight. A dye differs from a semiconductor absorption BHJ, and it only performs the absorption function and generally has no role in the transport. So what is actually done? You have a material like some material which is in contact. Over that material, a very thin layer of the dye, very thin layer. Normally, mostly it is monolayer of dye is, you can say, coated, and that is small monolayer only. Its job is only to absorb the light, and after absorption, the electron which is going after absorption in the dye will also have dye will definitely have some electronic levels. The electron will go into higher level. So as it reaches that level, it should be immediately be you can say removed from the higher level and leaving the whole level. So a dye difference, I show this when I show another animation. So a dye differs from a semiconductor absorber of bulk heterojunction, and it only performs the absorption function and generally has no role in the transport. For this reason, it is often referred as the sensitizer. In the dye semiconductor solar cell configuration, which is usually called as dye sensitized solar cell. So when you make an entire assembly, you have a semiconductor. Over that you deposit dye, and then you prepare the entire solar cell assembly. It is called dye sensitized solar cell. The dye is present in a monolayer on the semiconductor surface, so that charge from the dye may be easily transferred to the semiconductor. In a conventional dye sensitized solar cell, electrolyte with ion conduction instead of electrons is used for regeneration of the dye. So when you are in the liquid, in that case, what you have ions which moves, not an electron. So this is a like typical DSSC. So in this you have like a glass. Over that there is a FTO. Then you deposit TiO2 nanoparticles, and over those TiO2s, basically you deposit a dye. and that die is having this area is actually just showing the energy levels. There is no deposition. Die is deposited over these you can say balls only. So when photon falls, electron is excited in this die only from lower level to higher level, and then this is collected by this TiO2, and then it is transmitted through this and this. And then here you have a here we left with the hole, like, or not hole, if we can say this is the absence of electron here. So you have a redox couple. That is how you make is lithium iodide. Lithium iodide plus iodine. That is you chemists, you know very well what kind of electrolyte, redox electrolyte it is. So I will not go much into this. So it has I3 minus and 3I minus. So one electron from 3I minus is taken by this, and the time scale is low. So it is slow. This process is very fast. Electron reach here. It is collected by this TiO2. This is a very fast process, and this process is slow. Now again this 3I will get converted into I3 minus. So this I3, when this electron which was collected here, it moves through the entire circuit, it comes in the counter electrode at platinum, and then it is actually again it comes here, it is replenished, and I3 it becomes against I3 minus. So by this process, everything is completed and the SSC works in this way. So I will quickly go. Everything whatever I have explained, I have written very quickly for. So the same thing, like this part is in a slightly bigger way. It is shown here. So this is this ball, this TiO2, and over this TiO2, one dye is actually deposited in monolayer. So dye molecules are deposited. So you have now TiO2 which is covered with dye. Light will fall on this die and it will absorb. And then it will absorb the light, die will become excited. So it will electron will be in the excited state. And before it comes down to the ground state or recombine, it is, you can say, captured by this TiO2. Now after capturing this electron, it immediately transferred to this FTO surface here, and then FTO does, it reaches here through this FTO, and by this redox couple does the job of, like, first thing is that filling this electron, this whole panel absence of electron, and then minus. So let me go one by one. So this is typical redox lithium iodide and right. So this you know very well, that 3I minus and 2 electrons they give the 3I minus when is equal to 2E minus I3. It is a standard chemist lithium iodide iodine mixture reaction. And typical dye sensitized solar cells are giving efficiency of nearly 15%. So light enters through transparent. This I have already explained you in detail, and I will show in next slide an animation also. So everything will be clear to you. So the maximum voltage generated by such a cell is nearly about 0.7 volts for these reasons. And all of the processes in DSCs are kinetic. Their efficiency is determined how fast they occur relative to competing reverse process. So I will show you all competing processes here, and fabrication process also. So you have a FTO coated glass. So it was glass on this FTO is here, and there is no need for patterning. You just deposit a thin compact TiO2 layer over this. And after this deposition, you deposit, this is a very thin layer, just very thin. Then you deposit TiO2 nanoparticles in this way. So you have many nanoparticles now. And what is next procedure? Next, what we should be doing? All these nanoparticles should be coated with a dye, and preferably it's a monolayer of dye. So dye is in the liquid form. So you just put this entire assembly. This is called as photo anode also. This entire assembly you just dip in the dye. So what will happen? This TiO2 will absorb the dye and it will become like this. So imagine though there is some gap is there, but this is ideally all these should be covered with, and there should not be any direct contact with TiO2 with the electrolyte. Then after this, what happens? We bring a counter electrode, which was also some very thin platinum coating over there, and then you just bring them together to each other and then seal. The sealing is important because this is liquid. This electrolyte is in liquid form, so that is there is high probability that it leaks, so that you make a perfect sealing, and after sealing, then you make contacts. So one is counter electrode, another is this. Now let us see how. First, let us put energy levels and the light I2. This is this can go anywhere. So now these are just energy levels, just to explain. So if light falls, if light will fall on any of the die, suppose it falls on this die, or let us see, because it is in the close, suppose it falls on this die. So this die will absorb, and once it absorbs, what will happen? The electron will move from the higher. Now you just closely watch. There are three competing processes moving one by one. One is moving slow, another is moving fast. The electron is moving from where to where. I have already explained you everything. You just see and see which one is fast difference. Okay, you see the fastest is the electron capture from these two, TiO2. This is the slow. This is number 2, which this electron is captured by this hole, and this one is slowest when this electron comes from the counter electrode and it goes like this. So this is the typical working of the T1 transformation. Okay. So these are typical characteristics of the semiconductor which we use in DSSCs. Titanium oxide, TiO2, the particles which I showed. It is preferred because it is relatively inert, cheap, and has slow recombination of charge carriers. TiO2 has about 20 to 30 nanometer particles and band gap of about 3.2 eV. So imagine if it is having 3.2 eV band gap, what you can say spectrum range it will absorb. Just try to calculate. And N-type due to oxygen vacancies and has the typical thickness of 110 micron. TiO2 sintered to provide good contacts between particles. Transport of carriers in TiO2 occurs by diffusion. Diffusion length of carrier should be larger than thickness of the oxide. Obviously, carrier cell conduction band of TiO2 may be lost by reducing I3 minus by reaction I3 minus to 2 electrons. That is also possible, but probability is low that the conduction band TiO2 can also, because some part will be in the contact of dye, because you are not covering entire all the spares. There will be definitely some spares will be left. So there is a possibility of this bakery combination, but ultimately probability, you can say diffraction is less. It depends on how good you have fabricated the device. If you have made perfectly fine, then you will have about only 10 to 15% of the area which is left. The required characteristic for good dye are, it should be good absorption. It should have first thing, it should have good absorption on the metal oxide. There is actually no you can say bond. It is only absorbed on the surface. So the absorption should be good. It should stick to the surface, and there should be significant overlap with the solar spectrum. That is why that is only when you can absorb more amount of the spectrum. and more amount of absorbed spectrum will give you the more electron hole pair and more current. So eventually more efficiency. Fast kinetics of electron injection into TiO2 compared to recombination of dye by luminescence of non-radiative decay. Then it should be stable to many millions of cycles, so that it can have a long life. Then next comes is the preparation of photo anode and platinum counter anode. This is the actual process which we have followed in our laboratory. It is very easy to make dye sensitized solar cell. The making of bulk heterojunction is relatively difficult, though that is also easy as compared to DSSC. DSSC any student can make in her own lab without you can say putting much effort. So this I have written entire procedure of making with full details. If you want even time, if you have any doubt, you can email me. I will give you the full recipe. So in fact, whatever I have written is sufficient to make a license. So you read it. I will not read it. So these are different steps. So this is TiO2 deposition. When TiO2 deposited, then after that it is deep inside dye. This photo is not from our lab. This photo is from outside because it is. This photo it is more clear. It gives more picture. Then this is preparing the counter electrode of platinum coating by you deposit chloroplatinic acid and then fire it at about 450 degrees centigrade, and then it decomposes to the platinum, and a very thin layer of the platinum is formed over this glass, and then you can bring them together. Sealing is done like this. So then it was DSSC. What are the problems with the DSSC? The biggest problem with the DSSC is liquid electrolyte. So liquid electrolyte is it can leakage, it can evaporate also, and that is the problem everybody is facing, and that is the reason why the research on DSSC has reduced, because perfect sealing is not possible. And there is another problem, which is electrolyte degradation and hazardous nature of the components in this electrolyte. And then cost of platinum, even if it is very thin, you are using, but still platinum is expensive. So, and then stability is also poor. So these are some of the biggest problems. So what we can do, this all leads to the experiments of trying to make the solid state dye sensitized solar cell, where a solid state whole transporting layer was used in place of the liquid electrolyte. So it was almost similar. You have used one ETL layer, and then the same FTO, and then this TiO2 nanoparticles and dye, and then you use in place of this liquid electrolyte, you use a whole transporting material, which is a gel kind of. It was not completely solid, but so, and that is called Spiro, OMEPAD, and it is very expensive, and mostly it is imported and has a very high stability issues. Not very high stable, but stability issues. So every batch gives you a different result. So when you change this liquid electrolyte to solid one, this is called as the solid state dye sensitized solid state sensitized solar cell, SSC. Now in solid state dye sensitized solar cell, in this solar cell, liquid electrolyte is replaced with inorganic p-type semiconductor or organic hole conductor. A few other cases, polymer electrolyte, where conduction is by ions is used in place of the liquid electrolyte. These consist of mesoporous TiO2 with monolayers of dye and hole conducting materials penetrating into pores of TiO2. See, problem is when you use solid, see, you can have the structure in your mind. See, you have TiO2 structure, and then there is a lot of TiO2 spares are there. When you have liquid, it is very easy. Liquid can go very easily inside and fill all the pores and go on deposit on the all the TiO2 spares. But it will not be the case when we are using solid. So solid will not be flowing like a liquid and reach to entire thing. This is the problem with the solid state also. So what are these problems? As these are solid, filling of pores in TiO2 matrix is difficult, as I already said. Hole mobility in organic semiconductors is lower than that in electrolyte. And recombination of conduction band electrons of TiO2 is higher compared to the electron. So ideal hole transport material should have valence band slightly above the energy of oxidized dye. In the case of the perfect one, so but it is in spiral also. It is there is a little offset. So what happens if the band gap is matching exactly? Now what will happen? The electron. See, you had like this is structure. This is structure. The electron is already from this TiO2. TiO2 it has gone to FTO, and from FTO it has come through a circuit. Let us imagine it has reached and it is waiting here. Now, if you have a like energy level which was of the dye, this was ground level, this was excited level. So if there is a energy level which is here, and if this is matching with the medium where whatever you have filled, if it is also having same energy level, then it is this electron can very easily come and you can say fill this absence of electron, and circuit will be completed. So ideally we should have a valence band slightly above energy of oxide, or even if it is the energy level same energy level, then it is also fine. If it is slightly above, that is also fine, but it will not be there will not be more offset also. So some of hole conducting materials that have been commonly used as copper, bromide, and this is actually most commonly used, but mostly imported and expensive. Now next comes is the perovskite solar cell. So perovskite, if I say if I try to explain in a easiest way, in place of dye. Actually, this invention of, or you can say, discovery of perovskite cells was like that only. People were doing experiment in DSSC, and in place of dye, they used a material which was the structure of that material was of a perovskite structure. What is perovskite structure? This we know from the basic crystal structure. ABXC structure is a perovskite structure where you have A, B, and C are three. So the molecule which they have used as a dye was the methyl ammonium lead iodide, and it is having, because of this is having perovskite structure, and that's why these solar cells are called as perovskite solar. That is the reason why these are being called. So this material, which is this perovskite material, this was they were doing experiment for DSSC initially, and they found that it gave them encouraging results. So it eventually more experiments on this experiment led to several you can say worldwide several laboratories jumping into this, and this has become a separate class of the solar cells, and very promising class. And this is perovskite. What are the important property of this perovskite material? It is having a very high absorption coefficient. It can absorb its capability of absorbing the radiation is very high. Area mobility is very high, and about nearly 10 centimeters per whole second. And the diffusion length is also of the order of micron, and direct and tunable band gap. So you can with the structure you can change this band gap. So you can play a little bit of with the solar spectrum also. And these have high radiative efficiency, room temperature solution-based fabrication is possible. So with this, you can say this class of solar cells have grown, and it has become now a separate, though it was initially, it was, you can say, part of DSSC only. One can say the structure wise they are seen. I will just show in the next slide. So this is the crystal structure of this methyl iodide. Put in slightly more detail. The efficiency, present efficiency, this is actually old figure, so present efficiency nearly 27.6, 26.7%, which is the highest efficiency reported on the solar cell. However, you can see the DSSC, which led to the, you can say, birth of the PSS perovskite solar cell is only about 15 to 16%. So the deposition structures are like two planar structures and mesoscopic nanostructure. How we deposit these in most of these we use you can say gold transporting material. So there is actually no liquid electrolyte. So one typical, these are like I will explain one, other two you can just go through. So it is like in this, you have a glass substrate. Over that glass substrate, you have a TCO, transparent conducting oxide, which is FTO. So on that ion on that FTO, a small compact layer of TiO2 is deposited, which is this now. Which is what is there? That this is a small layer. You can see that is deposited. And over that, then there in place of TiO2, what is there? It is alumina, which is deposited. So you have alumina. This is the alumina, the white one. So you have alumina, and then over that alumina, the perovskite is deposited. And after that, you have a gold transporting material here. You have a gold transporting material here, and then the back contact. So with this back contact, you are now here contact with the you can say metal, make a contact with the metal, and they are also with this FTO. We got on FTO is what? This is transparent conducting oxide. So with this, one is this connection, one is this connection, and they are new putting on external load. So this is your one perovskite. So there are three different you can say perovskite you can say assemblies. Mesoscopic TiO2 infiltrated with biperovskite, and then planar PSCs without mesoscopic TiO2. This is also you can this the you can say assembly you can make. So we go work on the perovskite solar cell started in 2009, and as I already said, it is used as a sensitizer perovskite in the SFPs. Actually, some solid also. So it was material ammonium, methyl ammonium lead iodide, and this material is having perovskite structure. Perovskite structure, and that is why these are called as the perovskite structure. This is semiconductor with this is the band gap, typical band gap. Though this is I already said. So these are the some of the properties of the perovskite material. And theoretically, study shows that defect creates only shallow taps that do not force carriers to recombine. So that is also an advantage. So current best efficiency of perovskite solar cell is nearly 26.7%. Recent developments includes PSC made by dipping and spraying technique, and without PSC means perovskite solar cell. No? Made by dipping and spraying technique and without cold transporting layer, that simplifies the process. But those are actually all those are in experimental stages only. Though efficiency is very high, but still we are waiting for a reliable, commercially available perovskite solar cell. And because it contains lead, then there is another that is also an issue because lead itself is toxic. We are trying with king also, but not successful, very not so far. So most materials are the problem is. So most materials are inorganic, and that's like it is still we are in the, like, because materials are inorganic and therefore these are less likely to degrade as opposed to like in organic solar cell, pure organic solar cell, where degradation was main issue. And operation of nearly 1,000 hours has been carried out without noticeable degradation, which we have done in our lab also. So there are open issues in perovskite. Number one is hysteresis. Hysteresis is when actually you do IV measurements. When you scan from one you can say voltage to another voltage, then you will have a different current. However, when you come back on the following the same path, or coming in the reverse way, you get a different voltage. So it's kind of a strategy you get. The stability of device in the field need to be investigated. Replacement of toxic layer and many people have tried. It shows promise, but still the experimental stage only. Extensive degradation and the perovskites have been a lot of papers to see all the literature is filled with the perovskite papers. Then extensive degradation in presence of moisture, air, and temperature. That is also a big issue. Doping with chlorine and bromine ions and studies using other chlorine perovskites will be done. And these are pictures of perovskite solar cells which are fabricated at our laboratories. I just for that. And our efficiency of actually this is the old one, it's showing 14.75. We have reached nearly 19% efficiency in the solar cells. So now come to the another class, that is the quantum dots. So actually, if you have learned dye-sensitized solar cells, maybe it will be easy to explain that way. In place of dye, we use the quantum dots. What are the quantum dots? Quantum dots are very, you can say, where the size of clusters are very, you can say, small, and which is so small that the quantum effects are more dominant. How these are like made by different processes. Mostly the chemist knows how quantum works are there. Not go much into that. So colloidal quantum dots provide a varying band gap to optimally use the wide spectra of the solar radiation. So you vary the band gap depending upon the size of your clusters. So quantum dot provides possibility of multi-exciton generation as well as up and down conversion of photons. So since you are having a wide band gap, you can have all these possibilities. Semiconductor quantum dot materials, binary materials like lead sulfide, lead selenide, series cadmium selenide, and indium phosphide, etc. And ternary compounds such as cadmium, selenide, phosphide. These are used in the fabrication of quantum dots. And this synthesis of quantum dots is colloidal quantum dots of diameter 2 to 50 nanometer is carried out by using precursor compounds dissolved in the solution and organic surfactant. Temperature of process is critical. The fabrication process because so should be high enough to allow rearrangement of atoms, but low enough to have lower growth rate. And agglomeration is also a big issue that also need to be taken. So it is like you have now FTO, then there is small TiO2 barrier layer. There is compact layer we deposit in the case of DSSC also, in case of perovskite also, then we deposit TiO2. And then in place of now perovskite, what you have deposited is the quantum dots, small quantum dots. So and then so this is now on this side you have like gold or gold free, and then you can having working units. For best quantum solids available, the thickness of 1 micron is needed for absorption, while diffusion length is about 100 nanometers. So diffusion length is also fine. Therefore, bulk heterojunction type of structure is needed. Important materials like PiO2, zinc oxide, lead sulfide, bismuth sulfide, and this molybdenum oxide and other hole accepting materials, anti-reflection coating, etc. also deposited. So then this is like a typical quantum dot fabrication step. The glass over glass, then you have ITO coated glass. Now it becomes ITO coated glass, then deposit P dot PSF, then quantum dots of PCST quantum dot, you can say a quantum dot inside PCST. So you have a blend of P3ST and the quantum dots. You deposit them, as I said, like in other side, it's like a bulk heterojunction kind of structure. Then you have metal. So in this kind of typical thicknesses which we follow in our lab. We did some experiments and this HTL layer was approximately we deposited around 30 nanometer. This was varying for like 40 was the lowest, I think we went 100 nanometer also. And then so this was quantum dot solar cell. So typically, if you know basics of isosceles solar cell, then perovskite and quantum dots are almost similar. Only thing is sensitizer is different. So I have not gone in much detail on quantum dot solar cell, presuming that we have understood the concept. So if we go like best solar cell efficiencies, this is for with this actually this is basically the last slide for me photovoltaic. So we conclude all our photovoltaic lecture. So for single crystalline silicon, approximately 27.6 is the best efficiency. Gallium arsenide nearly 30.8, polycrystalline silicon 23.3, and CIGS solar cell 23.6, cadmium telluride around 23.1. This is amorphous hydrogenated silicon. Stabilized one is nearly 14%, and organic bulk heterojunction is it has achieved recently 19.2%. DSSC is somewhat saturated. For many years, there is not much progress, very gradually increasing. In like 10 years, only 1 to 2% has increased. And perovskite is increasing very fast. So now, currently, it is at 26.7% efficiency. And quantum dot solar cells are about 19.1. So, but all these values are actually for the laboratory scale. Only when you go for commercialized tools, which are at available in form of panel, which is very. So this is for the like modules which are available. The efficiency which I showed here, we are very much different than which are available in the form of panels. So if you have a crystalline, you get typically 10 to 17%. In polycrystalline, 10 to 13%. Amorphous, if you have hardly, you get 7%. Maximum 10%. Then gallium arsenide also in the form of when it is commercially available, you go for go and buy market. Then it is 18 to 30%. It's sweet is not 30, somewhere 20%. 30% is also for space quality when you are making buying from very expensive price, one can get up to that. DSSC, they are not very, you can say, stable for a very long time, but whatever are available can give the best 7 to 8%, and this is 2 to 3% only. And the life is also you will buy and they will not work for a longer time. This is the recent, actually today's on solar cell efficiencies data from the NREL site, and it shows that the best is here multi-junction solar cells which can multi-junction, so many solar cells with the at higher sun also, not at one sun density somewhere here. But this you can go through, you can access this their website. So with this, I come to the end of this lecture. And if you have any question, want to ask any question, I'm ready to answer. Any question? Well, if there are no questions, then let us close for the day. Thank you very much. See you day after on our fifth lecture. Thank you. Yes.